Let's try this out. Let's see if we can do it. I've got an airplane in the wind. And this airplane in the wind, it's actually some numbers that we've seen already, but we'll hash the whole thing out nice and friendly. I've got an airspeed for my plane, 420 meters per second. Actually, you know what? I want to go through and I want to fix this because I can't believe that I didn't fix this. Can we please just turn these meters per second into kilometers per hour? Because 420 meters per second is supersonic. It's faster than the speed of sound. I don't want to have that. Let's make it more realistic. Okay, let's bring it down to 420 kilometers per hour. Can't believe I missed that typo. Yeah, that would have been like just ridiculous.
Can you imagine the G-force acting on you?
I can't remember. I can't believe how that would feel. All right, so an airplane flies with an air velocity of 420 kilometers per hour, and I'm going to take note of what I know. The airspeed, remember it's slang for the velocity of the plane relative to the air. And the plane is observed to have a ground speed of 500 kilometers per hour. Now that's not a phrase that we've seen before, but what do you suppose it means? Velocity of plane relative to ground, yeah. In a direction of north 10 degrees east. And then there's a little note here, read the note. It says what I just said. The ground speed is slang for velocity of an object relative to the ground. Airspeed is slang for velocity of an object relative to the air. Wind speed or wind velocity is the way that most people talk about the velocity of the air relative to the ground. Okay, so a little bit of language there. What's the wind velocity in the airplane problem described above? Take stock of the givens. So let's take stock of the givens. I kind of like sketched things out already. Velocity of the plane relative to the air is 420 kilometers per hour. And the direction is north, 40.0 degrees east. Velocity of the plane relative to the ground is 500 kilometers per hour, north 10 degrees east. And then I want you to notice that none of these are like nice, pretty, just north-south kind of things. There's a wonky angle in both of them. So we've got to deal with that. And of course, it wants us to find the velocity of the air relative to the ground, the wind velocity. So the velocity of the air relative to the ground is, well, my unknown. But the first thing that I always want to do with these problems is write my vector equation. So the velocity of the plane relative to the ground is equal to the velocity of the plane relative to the air plus the velocity of the air relative to the ground. The next thing I want to do is do a little sketch underneath of my diagram, velocity of the plane relative to the ground. Well, that's 500 north 10 degrees east. Well, if this is my directional cross, north 10 degrees east kind of looks like this, you know? Velocity of plane relative to the air. Well, that's 420 north 40 degrees east. Well, that's kind of like that. And velocity of air relative to the ground, well, that's my mystery vector. Now, as I think this out, I think to myself, well, shoot. Sorry for the strong language. Velocity of the plane relative to the ground, that's my resultant. So I can't just add these two guys up to detail. I got to think about what my mystery vector is. Now, the nice thing about that is I have the resultant, so maybe I'll pull out my ruler. And if I'm sketching this, I know that my resultant, my double bolded vector, is going off like this. Maybe I didn't quite get the angle right. But I also know that this shorter vector is going off a little bit more to the east. Something like this. And even though I have no sense of how airplanes work, I know that this vector, boom, plus a mystery vector adds tip to tail to give me the velocity of the plane relative to the ground. And as soon as I do that, obviously if I do a better scale diagram, I'll have a better approximation of things. But can you guys see that the missing vector has to go right here? It has to. And I know nothing about airplanes. Like really, I'm very ignorant about all this stuff, right? I'm a canoeer. I'm not a plane flyer. They call those people pilots. Yep. So I would say, hey, look, this mystery vector got to go off like this. It's got to. There's no other option. It's got to complete the vector equation. So even again, in my ignorance, I know that it's got to look like that. So I can label things up. I can say velocity of the plane relative to the air is that one. Velocity of the plane the air relative to the ground is this one. And the velocity of the plane relative to the ground is this one. And if I wanted to add in a few more sketch pieces of information, I know that the velocity of the plane relative to the air was north 40 degrees east. Now that means that this angle is north 40 degrees east. Notice that that angle cuts through my shape. I find that visually confusing because I'm a very simple person. But look at this. If that arc is 40 degrees, doesn't that mean that this arc is what? 50 degrees. That doesn't cut through my shape. Velocity of the plane relative to the ground, I'll do a different color. That's 10 degrees, right? Does that cut through my shape? No, that's what people would call an exterior angle. That's 10 degrees. And so I can do a little dotted line there. Now that's useful. The reason it's useful, as we saw in the previous little quick segment, is that that means that I can construct a right angle triangle that's exterior to the interior triangle, so that I have a y component and an x component for each of those vectors, treating them like a hypotenuse, and that'll allow me to use SOHCAHTOA and Pythagorean theorem to investigate this thing, right? And again, as I'm thinking this out, I know that this yellow one here and this yellow one here are going to be related to the invisible yellow one right here. See this guy right here? Aren't they all going to add up? And then again, I'll use my pink highlighter. This pink one here and this pink one here are going to be related to this pink one, which is invisible right now. But I'll add it in. And I know that it's got to go over to the west, that amount. Okay? So getting my sides, my perpendicular sides, exterior to that triangle really helps. It's a problem-solving strategy, and it's a problem-solving strategy that's going to allow us to sidestep sine law and cosine law. It also, if I'm a big picture thinker, which I try to be, it means that later on, as I get more mature in this stuff, I could write a spreadsheet to solve all these things. I could write software, really easy to solve all these things. Writing software for sine law and cosine law for free-floating triangles is trickier than perpendicularizing the world and making x and y columns. That's just a fact. Okay? So I want to make sure that we're set up as problem solvers to go beyond grade 11, and we're setting a foundation. The first person that tells me that I hate sine law or cosine law, I'll call you a liar. Why would I hate such a thing? Right? It's beautiful. Don't go tell your math teacher that I don't believe in it or something like that. I'm teaching an alternate strategy, and a very good strategy. Everybody understand what I'm saying? Okay, cool. So this was just my sketch. This is my brainstorm. Now we're ready to get down into the dirty business of solving. And I need everybody to whip out their calculators because I'm going to be asking for numbers, okay? And we got to start adding on some details onto this thing. Now I made my diagram as big as I could so that I could add in the details. This vector here we declared was going to be the resultant, so I'll double it up. This is my velocity of the plane relative to the ground. This vector over here, that's what we ended up calling the velocity of the air relative to the ground. Velocity of the plane relative to the air. And those guys are adding up tip to tail. Boom, boom. Velocity of plane relative to the air had a magnitude of 420 kilometers per hour. Velocity of the air relative to the ground, we don't know the magnitude. Velocity of the plane relative to the ground is 500 kilometers per hour. We already deduced the angles for the exterior shape. We were given straight up that this is 10 degrees. I know that it's not to scale, and I'm not stressed about it. And we figured out that this is 50 degrees. In math class, we're always obsessed with the interior angles, but this time we're going to think about the exterior angles. Different way of thinking. Not more right or wrong. And then we say, all right, That VPA had an x component. I'll call it VPAX. And it's equal to VPA times cos of 50 degrees. It's got a y component. I'll get my ruler out of the way, don't worry. It's got a y component. Of course, this is a right angle triangle because x's and y's are at right angles to each other by definition. So VPA y is equal to VPA times sine 50 degrees. Again, just a SOHCAHTOA statement because we know the hypotenuse and we know the 50 degrees. Up here, we can deal with our top left-hand corner triangle. And again, I'll get my hands out of the way in just a minute. We've got our y component. We've got our x component for VPG. And we appropriately call them VPG y and VPG x. And they would have the formulas. Notice that I won't just use cos for x components. I got to think about what's the actual adjacent. So in this case, it's VPGY that gets the cos because it's the adjacent. So VPG sine 10 and VPGX is VPG cos 10. And the missing information, well, the reason I'm doing all this is so that I can go through the process to figure out the y component and the x component for VAG. So VAG x and VAG y. And if it's helpful, you guys tell me, is it helpful to have the pinks and the yellows? I'll put some pink and yellow on there, just like to make sure that we got it, okay? So these guys here, all these pink ones, are related to each other because they should add up, right? This yellow plus this yellow should add up to this yellow. And in terms of how we're going to lay out our page, I want to be a spreadsheet thinker. And as a spreadsheet thinker, I'm going to have an X column and a Y column. My X column of information is going to be all about those yellow lines. Of course, yeah, we really should have like a north, south, east, west. And we can make north be positive and east be positive. Doesn't really matter. It will be consistent. And in the X column, the pink information, we could say VPAX equals VPA times cos 50 degrees. That's the 420 kilometers per hour times cos 50. I'm just going to tell you, I've done the math on this one already. Is it okay if I just write down the answer for what that is? We'll just short circuit it a little bit, okay? You end up getting 269.97 kilometers per hour. If I do the y component for that guy, I get VPA y is the VPA times sine 50. Again, I plug in my 420, my sine 50. And again, I did the legwork on this one earlier. I get 321.74 kilometers per hour. And if you check my work and you tell me I got something wrong, I'm open to criticism. That's okay. But you know, I really am going to be a spreadsheet kind of guy here. I want to make columns. I want to make rows. And I want to say, for VPG, there's a VPGX. And VPGX is going to be VPG times cos 10, or 500 kilometers per hour times cos 10. Again, I've done the math on this. I get 86.82 kilometers per hour. And then for the y component, I get VPG y equals VPG times sine of 10 degrees. Oh, did I mess that up? That should have been a sign. Nobody said anything. I did still get the right answer, don't worry. I just wrote it down incorrectly. Sine, sine.
What about the other one?
That should be cos. In my haste, I'm sorry. I can see a couple people frustrated, but nobody spoke up. Cos, 10 degrees. 500 kilometers per hour. And cos 10 degrees. And we end up getting 492.4. People say, well, why did we do all that? Yeah. So I want you to notice, we just found this pink length and this pink length. Those are the x's. That's this column. Pink. We just found the pink stuff. We just found the yellow stuff. Right? And you can go back and you can label those numbers if you want to, if it helps you to feel more confident with what we're going to do next. Because then we would say, okay, well that means that VAGX is going to be equal to, oh, it looks like VPAX minus VPGX, or 269.97 kilometers per hour, minus 86.82 kilometers per hour.
Oh, yeah. Yeah.
And VAGY
Drew, you get it?
is going to be VPGY minus VPAY, or the 492.40 kilometers per hour, minus 321.74 kilometers per hour. And that gives us 170.66 kilometers per hour. Now, again, point out what we just figured out, this, oh, I didn't write the last line, 183.15 kilometers per hour. What we just figured out, this pink one and this yellow one, are respectively this pink side over here and this yellow side over here for this triangle. Now at that point, all we got to do is use Pythagorean theorem and SOHCAHTOA. I got this and this. I got VAGY, VAGX. Slide it up. VAGY, yellow, VAGX, pink, and the hypotenuse, VAG. I've taken that vector up here and pulled it down here, and we've got the x component, and we've got the y component. And we should be able to pull this together to figure out the theta value and the hypotenuse. Okay? Now if you do that, the theta value and the hypotenuse, you guys mind if I just, you can take a screenshot if you need to. Can I put the Pythagorean theorem and SOHCAHTOA up on the screen for you? Because really we're just pulling these two things together. And it looks like this. Okay?
Hold on. I'm gonna use this later.
Let's be really clear. I'll color code it again to make sure we're still speaking the same language, even though this is some writing that I wrote down earlier. I've got my x1 here. This is the same x value. This is my same y value over here. We're going to use Pythagorean theorem to get VAG. We're going to use SOHCAHTOA to get the angle. And in the end, we go up at 250 kilometers per hour, north 47 degrees west.
Understood. We should do a class.
And sadly, I can't make it like a whole lot
give you a cookie, but
quicker. Okay?
we all get it. Are you gonna use that one?
Yeah.
Wait, can you take the sticky notes off?
Take the sticky notes off. Yeah.
I didn't get why. Okay.